Today we are going to discuss force on a moving charge in a uniform magnetic field. What is the expression for the force on the charge? On what factors it depends? Then we'll see how we can find the direction of this force. After that, we will discuss what is Lorentz magnetic force and Lorentz equation. Then, what is the path of the charged particle in uniform magnetic field under different cases? And finally, we'll discuss the details of the cyclotron. What is cyclotron? On what principle it works? What is its theory? What is its working? What is its construction? And what are the limitations of cyclotron? All these we'll discuss in today's discussion. Let's first take force on a charge in uniform magnetic field. And that charge also should be a moving charge. Now, why should a moving charge experience force due to magnetic field? Now, we have seen that if you have a current element, it produces magnetic field. And if you have two current carrying conductor, in that case, if they are kept at some separation, the field produced by one conductor will exert a force on the other conductor which is carrying current. So here also, if you take a charge moving with certain velocity, in that case, we can treat that one also as a small current element. Because the current, if you are taking, it is the flow of the charge. And if you take a small length of the current carrying conductor, then that is your current element. Similarly, if you have a charge moving with certain velocity, then dimensionally you will find that it is same as that of a current element. So let's first of all take what is force experienced by a moving charge. Force experienced by a moving charge is directly proportional to magnitude of the charge. It is directly proportional to the velocity of the charge. It is directly proportional to magnitude of the magnetic field in which the charge is moving, and is directly proportional to sine of the angle between the direction of the velocity and magnetic field. So if all we take there, then we have force F experienced by a charge Q, which is moving with velocity V in the region of magnetic field B, then F will be directly proportional to Q, directly proportional to V, directly proportional to B, and directly proportional to sine theta, where theta will be the angle between the direction of velocity and magnetic field. Suppose we have a charge Q, which is moving with velocity V, and we have magnetic field in this direction. In that case, if theta is the angle between the two, then it will be proportional to sine of this angle. If you combine all these, we can get F proportional to QVB sine theta, or F can be written as your KQVB sine theta, where this K is a proportionality constant. And if you consider that the terms have been defined in such a way that K is 1, if K is 1, and how we are getting that? We are defining the terms in such a way that this K is 1. That means we take Q 1 unit, V 1 unit, B 1 unit, sine theta also we take it as 1, and whatever force the charge experiences, F, that also if we take it as 1, that means we define force in that way that whatever we are getting, the magnitude there, that we take it as 1 unit. And if we take that, then K will be 1. And in that particular case, F will be equals to QVB sine theta. So this is the expression for force on the moving charge. If you write in vector form, then F can be written as Q V cross B. So this is the expression for the force experienced by a charge moving with velocity V in a region of magnetic field B. Now, since it is a vector quantity, so we need to find the direction of this force. For that, you can see it is the cross product of V and B. So if it is the cross product of V and B, then we can take help of either right hand screw rule or right hand thumb rule to get the direction of this cross product. And right hand screw rule is there. If you assume as if you have a right-handed screw held perpendicular to the plane containing the two vectors. So here, if it is V is there, B is in this direction, we'll put a right-handed screw perpendicular to the plane containing the two with its tip at the common point. And we'll rotate it from first vector to second. That means it is V cross B. So we'll rotate it from V to B through a smaller angle. So if you do in that way, that means if you are rotating a screw in this direction, that means you are rotating in the anti-clockwise direction, then in this case, F will be directed out of the plane. Because if you are rotating a screw in anti-clockwise direction, the tip of the screw will come out of the plane. So F will be directed out of the plane. Or if you consider that V is in this direction, B is here, and theta is the angle between the two. Now, if you take V cross B, so for this case, V cross B, for the force, now we'll rotate it from V to B through a smaller angle. So it is being rotated in the clockwise direction. So the direction of the force will be directed into the plane. So this is directed into the plane. Now here, this is the best way to find the direction of the force as the cross product of two vectors. However, if suppose the velocity is perpendicular to the magnetic field, in that case, you can apply Fleming's left-hand rule there. In that, we stretch forefinger, middle finger, and thumb of left hand mutually perpendicular. We keep the forefinger in the direction of the magnetic field, middle finger in the direction of the velocity of the charge, then thumb will indicate the direction of the force. So that is there when the two, that is the velocity and the magnetic field, are mutually perpendicular. If it is not perpendicular, in that case, you can simply apply a cross product of vector that is there. You take help of the right hand thumb rule, right hand screw rule, and get the direction of the force. Force experienced by the moving charge in the uniform magnetic field, what we write it as F equals to Q V cross B. This is called Lorentz magnetic force. So here, if you just take its magnitude, we can write QVB sine theta. Now here, if you consider Q is 0, then F will be 0. That means an uncharged particle will not experience any force in magnetic field. That means if your neutron is there, it will not experience any force in magnetic field. Now, does it mean all charged particles will experience force? Let's see. If Q is not 0, it is a charged particle, but V is 0, then again force will be 0. That means a charged particle at rest will also not experience any net force due to magnetic field. Again, we can say, is it that all moving charged particle will experience force in magnetic field? A static charge will not experience force. But if suppose it is a moving charge, will it experience force? So again, we can take third case. If Q is not 0, V is not 0, but sine theta is 0. That means theta is 0. Then also F will be 0. That means if you have a charge moving with certain velocity, but in the direction of magnetic field, either in the direction of magnetic field or maybe in opposite direction of magnetic field, it will not experience any force due to magnetic field. So these are certain cases. That means if any statement is there, just read the statement carefully before you answer for any conceptual type or objective type questions. So this will be the different cases what we get using the formula F equals to QVB sine theta. And of course here, if we take, if theta is pi by 2, then F is equals to QVB sine pi by 2, and that is your QVB. Remember, the maximum value of this is 1 that we have taken. So here also this will give you maximum value of force. So we'll have maximum force experienced by a charged particle when theta is pi by 2. Then force experienced by the charged particle will be maximum. Let's now take nature of the path of the charged particle in magnetic field. What type of path the charged particle will possess? Here, first case if you take, if theta is 0. Now in this case, the force will be 0. So that means if you have charged particle moving in the direction of magnetic field, it will not experience any force there. And if it does not experience any force, it will continue to move with its own velocity. That means here the path will be a straight line. Let's take second case. If theta is pi by 2, that means here we take, suppose the charged particle is moving in perpendicular direction to magnetic field. This is pi by 2. So now if this is pi by 2, the force which will act, as it is the cross product of V and B, so the direction of the force is perpendicular to this V and B. So in that case, the charge will move in such a way that the force which is acting on it will make it move along a circular path. So it will move along a circular path because at all moment, the force is perpendicular to the velocity. So it will try to move it in a circular path there. So it will move in circular path. So this will make the path of the charge in magnetic field as circular. Now, if theta is acute, that means this time we are taking that magnetic field is in this direction and velocity V is at some angle. So if V is at some angle, in that case what will happen? Here in this case, the charged particle as it is moving there in this region, we can take the velocity and resolve it into two components. One is say parallel component, which is your V cos theta, and other is the perpendicular component, which is your V sin theta. So now what will happen? Due to this V cos theta, there is no force experienced by the charged particle in the magnetic field. But due to this V sin theta, it will definitely experience force. and that force will make it move in a circular path. So due to this V sin theta, it will move in circular path, but due to V cos theta, it will also tend to move in a straight line path. So its path will be finally a helical path, because in this case it will have the circular motion as well as a translational one. So for this, the force which will make it move in the circular path, that is your QVB sin theta, and the centripetal force acting there, or you can use m omega square r also for QVB sin theta. From this we can get the time period, we can get the frequency of revolution. Here pitch will be equals to the velocity component in this direction, that is your V parallel multiplied by time period of revolution, and V parallel will be your V cos theta, and the time period we can calculate from this one. Omega will be your 2 pi by t. So substitute that, you will get this expression for the pitch. So from this you can calculate what will be the pitch of the charged particle. Say that it will have the helical path in this case. So these are the certain things which we get for the path of the charged particle in magnetic field. Now if we consider what is the work done by the charge in magnetic field, is there any work done there on the charge? Here force is there. There is a force acting on the charged particle due to the magnetic field. So force is acting there. It is also in motion. So is there any work done? No. Work done is 0. Why it is 0? Because the force due to magnetic field will be acting perpendicular to the direction of the displacement there. Displacement in the sense you can take at all different points, as the force will be always directed towards the center of the circular path, and the displacement of the charged particle will always be in the tangential direction. So the angle will be 90 degree there. So if the angle is 90, in that case the work done you can take, it will be 0. Now that you can prove also, like if I take the force on the charge, it is your QV cross B. This is the expression for the force. If you want to find out the work done, in that case the small work done we can take as the dot product of force and displacement, and this we can write as force dot. Now displacement we can get if you take the velocity and you multiply it by the small time interval in which that displacement takes place. So it is your F dot V dt. This will be your Q V cross B dot V delta T. Now you see V cross B will be perpendicular to the plane containing V and B. So it is perpendicular to V and B. And now if you are taking dot product with V, in that case the angle between V cross B and V is 90 degree. So if you take dot product, it will be cos of the angle between the two. So it is your cos pi by 2. So in that case it will be 0. So this will be 0. This we can also get if you consider that delta W can be written as your Q delta T, and now it is your V cross B dot V. That means this is your basically V B V, a scalar triple product. And if you take a scalar triple product, in that case, if in the scalar triple product two terms are same, in that case the scalar triple product value is 0. So in this case, this will be 0. So that will also show that the work done will be 0. And if work done is 0, if you apply work energy theorem, work done is equals to change in the mechanical energy. Here if you take the change in the kinetic energy. So as the work done is 0, there is no change in kinetic energy. No change in kinetic energy means speed will remain same. Here the velocity, if you consider at different points in the circular path, will be acting tangentially at those points. So they will have the different directions. But magnitude, if you take, it will be 0. It will be constant there. So it will have the constant speed. Direction will be different at different points. But since the magnitude is same, that means the speed is same. That is why there is no work done. Now let's take motion of the charged particle in a region of electric and magnetic field both. There is a region in which electric field is there as well as magnetic field. So what is the force experienced by the charge in that? Suppose I assume that E is the electric field, B is the magnetic field in the region where the charge Q is in motion. So the force experienced by the charge due to electric field, that if I represent it as Fe, it is your QE. Force experienced by charge due to magnetic field, if I write it as Fm, it is your QV cross B. So the net force experienced by the charge, that will be equals to Fe plus Fm, and that is your QE plus V cross B. This is the expression for the force. And this equation, we call it as the Lorentz equation. The force is also the Lorentz force. If only this term is there, FQV cross B, that is the Lorentz magnetic force. And this is the general Lorentz equation there for the charge which is experiencing force there in the region of electric and magnetic field both. Now we may have the cases there where the value of the electric and magnetic field, their directions are such that the charge is moving undeviated. If it is given in that the charge is moving undeviated in a region of electric and magnetic field, it simply means the net force experienced by the charge is 0. And if the net force experienced by the charge is 0, in that case, here, if F is 0, it also means QE plus V cross B. This is 0. And if this is 0, that also indicates that E vector is minus V cross B. So, you can use this one. We know that direction has to be opposite. And if you calculate for the magnitude, E will be your minus VB sine theta. So if it is asked with what velocity it should move, at what angle it should move, you can take help of this equation and find out that what should be the velocity or at what angle it should move, so that it goes undeviated or it does not experience any net force in a region of electric and magnetic field. Now let's discuss cyclotron. Cyclotron is a device which is used to accelerate charged particles so that they acquire high velocity. These energized charged particles can be used for different purposes. They can be used to initiate some nuclear reaction there. They can be used to bombard any target there. So these are used, charged particles are used for different purposes. It works on the principle of synchronous motion of charged particle in a region of crossed electric and magnetic field. we have a region in which electric and magnetic field both are acting there in perpendicular direction. So by making the charge move in that particular region of electric field repeatedly, we can accelerate charged particle. So that will be more clear if you go through its working, you go through its construction, how the charged particle is accelerated. So let's first of all see its construction. In its construction, we have N and S representing pole pieces of the magnet, which is used to produce magnetic field. D1 and D2 are two semi-cylindrical hollow conductors, and they are called as Ds. Okay, we call them as Ds. These two are placed in the region of the magnetic field produced by these pole pieces of the magnet. So suppose we have one pole of the magnet here, another is below. That means magnetic field will be acting in this direction. Suppose it is the z-axis. Here, these two Ds will be kept in the xy plane, so that the magnetic field is perpendicular to their plane in which they are kept. And these two Ds are kept at some separation, and a high frequency oscillator is connected to these two Ds. W represents the window through which the accelerated charged particle will finally come out. Here, we take suppose a point O, where the charged particle will be released in the gap between the two Ds. Now let's see how it works. So let's discuss its working. Now for that, suppose we just represent these two Ds, like this is one D, this is the another one, this is suppose D1, this is D2, and these two are connected to high frequency oscillator. There is a little gap between the two, and due to this high frequency oscillator, there will be an electric field produced between the gap of the two. I think magnetic field is perpendicular to the plane of the board. So magnetic field is perpendicular to the plane of Ds. That means in this case it is perpendicular to the plane of the board. Now if I take a charge which is released between the gap of the two Ds, suppose the charge is Q. As there is, it is connected to high frequency oscillator, so there will be electric field between the gap of the D. So this charged particle will experience force due to the field which is applied, and it will get accelerated. Let's assume that at any moment D2 is at positive potential and D1 is at negative potential. So if our released charge is positive, it will experience force in the gap between the two in this direction, say from right to left. So it will move as it will be accelerated due to the electric field. So it will enter one of the Ds, say D1, with velocity, say V1. It has started with zero velocity, gets accelerated and enters inside the D1 with velocity V1. So there, the moment it enters inside the D, there will be no effect of electric field now, because electric field inside a hollow conductor is zero. But magnetic field will be acting there. So the charged particle will now experience force due to magnetic field. And due to this, as the field and the velocity are mutually perpendicular, it will follow a circular path. So it will move in a circular path, and just due to this specific shape of the D, just after completing half circle, it will come out. But since there is no change in the speed, so if it has entered with speed V1, it will come out with the same speed V1. The polarity of this oscillator, or the frequency of the oscillator, is so taken that by the time it comes out of it, the polarity gets changed. Now this is positive, this is negative. So that in this gap, again this charge will get accelerated. And now it will enter, as it gets accelerated, it will enter second D with the velocity v2. Because in this gap there will be electric field, it will get accelerated due to that field, and it will enter second D with increased velocity, and due to which it will follow again a semicircular path. Again it comes out here with speed v2. Again the polarity gets changed. Now this will be negative, this is positive. Again it gets accelerated, now it enters with the velocity v3. So this way again it will describe a semicircular path. Radius will go on increasing. So that is how the charged particle will be increasing its velocity. It will move in a circular path of greater and greater radius and will finally come out of this cyclotron or the D's of the cyclotron. And we will have those accelerated charged particles which are energized, available for our purposes. This is how the cyclotron works. Now here just remember, we say synchronous motion just in this way, that by the time it completes its revolution inside the D and it comes out, or the polarity gets changed. Because if the polarity does not get changed, in that case it will experience force in the backward direction, which will not make it accelerated throughout the motion. So it will not increase the velocity continuously. So this is the reason why the polarity should get changed once it comes out of the D and enters in the gap between the D's. So this is how the charged particle gets accelerated inside the cyclotron. Let's take now theory of cyclotron, how the charged particle get accelerated, what will be its frequency of revolution, and what is the maximum kinetic energy which they can possess. So suppose we have the charge Q of mass m moving with velocity v in the region of magnetic field B. And there it describes a circular path of radius r. So the force due to magnetic field, this F is your QVB sine pi by 2, because V and B are mutually perpendicular. So it is your QVB sine pi by 2, or it is your QVB. The centripetal force, that will be mv square by r. Therefore, as centripetal force will be provided by this force due to magnetic field, so in this case F will be equals to mv square by r, or QVB. This is your mv square by r, or V is equals to QBr by m. So this indicates that the velocity will be QBr by m. Now for a given charge in a region of particular magnetic field, its mass is fixed. So what you will find, that V will be directly proportional to r. That means if the velocity is more, the radius of the path will be more. That is why we have seen, if the velocity is changing from v1 to v2, the radius of the circular path is also changing there. Now let's take time taken inside D. Time taken inside D. How will you find that? What is the length of the path described? Length of the path inside the D is pi r, because it is describing a semicircular path. So length is pi r and speed is v. So this will give the time taken. Now if I put the value of v from this one, so we have pi r by QBr by m, and that is your pi m by QB. There it is describing semicircular path. as it is describing semicircular path, so obviously we can say that the time period will be double of this time. So time period of revolution that will be 2 pi m by qb. Now, if this is the time period of revolution, then frequency of revolution, that is 1 by time period, and that will be equals to qb by 2 pi m. This is also called cyclotron frequency. Remember, this will also be the frequency of this oscillator. Then only it will have the synchronized motion. So this is the expression for the time period or frequency of revolution. And we can also see here that the time period does not depend upon the velocity. It only depends upon the mass, charge, and magnetic field. Because velocity, if the velocity or the speed is more, radius is also more. So that is why you'll find that time period term will be independent of that quantity. Next is maximum kinetic energy possessed by the charged particle. That means in the cyclotron, how much maximum energy the charged particle can possess. So maximum kinetic energy of the charged particle, that will be maximum value of the kinetic energy. So it is your half mv square maximum value. That is your half m. Now for the velocity, the expression was qbr by m. So it is a square of this quantity and then we take its maximum value. So this will be equals to half q square b square r max square by m. So this is the maximum kinetic energy possessed by the charged particle in a given cyclotron. Charge will be fixed, B will be fixed, M will have fixed value. And also R maximum. R maximum will be the maximum value of the radius of the orbit of the charged particle. And what will be that maximum value? That will be equals to the radius of the D of the cyclotron. So with that, we can find what is the maximum kinetic energy of the charged particle in a cyclotron. Let's now take limitations of cyclotron. The first limitation is that it cannot be used to accelerate uncharged particles like neutrons. Because if it is uncharged, definitely it will not experience force due to magnetic field. And in that case, it cannot be put into motion where we can accelerate them. So cannot be used for uncharged particles like neutrons. Second, there is a limit up to which we can accelerate charged particle. We cannot accelerate charged particle infinitely. Now, why we are saying that there is a limit up to which charge can be accelerated? Because due to the theory of relativity, mass of a particle changes with velocity. This is given here. M equals to m naught divided by root over 1 minus v square by c square, where m naught is the rest mass, m is the mass of the charged particle, when mass of the particle when it is moving with velocity v, v is the velocity of the charged particle, c is the speed of light. Now here, if the charged particle is moving there with certain velocity and velocity approaches to speed of light or becomes comparable with the speed of light, where mass will change appreciably, and if the mass changes appreciably, then the frequency which was your qb by 2 pi m. Here, if the mass is changing, the frequency will not remain constant. So the motion will not remain synchronous. So this is the reason why there is a limit up to which we can accelerate, because beyond that if you go, then the change in the mass we cannot neglect, then it will not remain synchronous motion. Third, it cannot be used for light charged particles like electrons. Cannot be used for light charge particles like electrons. Why we cannot use it for accelerating charged particles like electron, light charged particles like electrons? Because if you consider electron and proton together in a particular electric field, as the charge is same on both, force experienced by the two will be same. But due to different masses, they will experience different amount of acceleration. And we know that mass of the electron is about 1837 times mass of the proton, nearly 2000 times less. So acceleration of the electron, if you consider, it will be very large as compared to acceleration of the proton. It will be 2000 times more than that of the proton. And if the acceleration is very large, then within a very short interval of time, it will acquire very high velocity where the change in mass cannot be neglected. And if the mass changes, then frequency will change. And if the frequency of revolution changes, the motion will not remain synchronous. So it cannot be used to accelerate charged particles. Are some of the limitations of cyclotron. This is all about the details of the cyclotron.